Hey guys, you're watching Python tutorial videos on my YouTube channel Python for Microscopists. This video is a continuation of our discussion about autoencoders, and of course in one of our previous tutorials we talked about the basics of autoencoders, and in the last three videos we looked at a few applications of autoencoders including denoising, anomaly detection, and in the last tutorial we actually looked at domain adaptation where we converted Einstein image into Mona Lisa image by tricking the autoencoder during the training process. So let's use the same tricky method to artificially colorize black and white images or grayscale images. And again, the way it works is, just to remind you again, a quick note about autoencoders. It's nothing but we are training the image on an image and reconstructing it back, the original image back. In other words, we are fitting a model of x and x, where x is our input and it's also the output. Now obviously during this process there will be some reconstruction errors, meaning our output is never going to be looking exactly like our input, okay, in this process. Now the reason why again is we are taking a high pixel density image, pixel resolution image, in this case let's say 256 by 256 image, and then downscaling it down to 32 by 32 or even 16 by 16, sometimes 8 by 8, and then upscaling it back to its original size. And in this process we are training the weights and and adjusting the biases, which is what we call a trained model. Okay, and we apply this model to other images. So in the case of noise reduction, our x was a noisy image and the second x was a clean image. I should have actually changed this to x and y, but I thought x and x would make it easy for me to communicate. But think of this as x and y, where y equals to x. That's autoencoder. Okay, now for noise reduction, our x is a noisy image and y is the clean image. And for anomaly detection, we trained the model autoencoder on a whole bunch of good data or non-anomaly data, if that's a term, and reconstructed the original data during the training process. And then we said, okay, any large reconstruction errors, we're just calling that data anomaly. Okay, and for image colorization, we actually trained this autoencoder on a whole bunch of grayscale, on a whole bunch of this is not an image colorization, sorry. For domain adaptation, we trained this autoencoder on one type of image and tricking it that, okay, my y is not equal to x, but my y is actually Mona Lisa. So once you train it on a bunch of images, then you can supply any random Einstein image in the hope that it would reconstruct a Mona Lisa image, matching whatever that Einstein image that you supplied was. And finally, image colorization. We actually, what we plan on actually doing is taking a grayscale image and supplying corresponding color image, and training the algorithm or training the autoencoder and creating a model that learns how to colorize other images. So instead of doing this on one image, let's actually download a whole bunch of images from the internet and then use those for training. Or if you can find image data sets, again there are a lot of websites where you can, Kaggle is probably one of the primary ones, where you can download some data sets that you can use for this purpose. So let me jump on to the code itself, and again let me minimize, these are the windows from previous tutorial, but let's jump into the code itself. And by the way, just to show you what input images we are actually working with, let me open the folder. And here is the folder for colorization. So I dumped all my color images in this folder, and instead of converting these into grayscale using a different application or something, the way I'm going to do is load the color images, convert them into grayscale, and then train this autoencoder on the grayscale images, and then we will have our corresponding color images anyway here. So that's the trick here. Now, how did I get all of these images? Again, one way is to download them from one of the standard websites that actually give have a big repository of these images, or in this case I used these 4 lines of code to actually go to Google image search, and then I searched for national parks, dog park, and I also searched for barn earlier, and then I set a limit of 100 and dumped all those images into my folder down here. That's one easy way of actually getting a whole bunch of images. And obviously all the images are going to be in some random size, so I resized all these images using a code, or by the way, we can actually resize these images as part of our main code anyway. So anyway, so get a whole bunch of images, dump them into a folder, right? And then we are all set to start. Okay, so the first line, obviously we are defining the path to our images, and then we are going to resize images to, well, rescale images by dividing every pixel value by 255. Again, these images are all color images. They are in the RGB space, red, green, and blue, meaning each image has 3 channels, right? One for red, one for green, one for blue. And each of those pixel values in each channel, we are dividing it by 255. And why are we doing this? Because we want to normalize all our pixel values to values between 0 and 1. Okay, and the primary reason why we do that, especially for these type of deep learning neural networks, is the activation function. For example, you know, we are using ReLU activation function, and this function actually goes from 0 to 1. In fact, I believe I have right there. You know, you can look at the documentation for ReLU activation function, but you can see how it's going from 0 to 1, right? So that's why we need to rescale all the pixel values to between 0 to 1, and that's exactly why I'm doing this step. And then my input images are of various sizes because I downloaded them from Google, so we need to resize them to the same size. So this is the next step here, is to actually resize them to 256 by 256. And if you have lots of images, it's very important for you to define a batch size, so the images are loaded into memory in batches and then processed. Okay, now this part is a bit important for this specific exercise, for image colorization exercise, because you can work on RGB images. I mean, we are working on color images anyway, so you can work in the RGB space, which is red, green, and blue space, meaning every image is very important, right? So, well, every channel is very important in that case, and you need to predict values in every channel. So instead of doing that, I think for this exercise, one way, or one easy way to handle this, is by converting our RGB image into lab space, LAB. Okay. Now, just a quick explanation of lab. That's the screen I had earlier here. So L stands for lightness. How light is the image, right? So think of this as the gray level image, or black and white image, if you prefer that term. Yeah. So if you only look at the L channel, the image looks like a black and white image. On top of that L channel, you actually add A and B. So in this specific graphic, A is represented along the x-axis, okay? Meaning A actually goes from green to red, and B goes from yellow to blue, or blue to yellow, if you want to call it. Okay, so this is your blue axis, this is your this is your B axis, this is your A axis. So we are dividing our image, or we are converting our RGB image into lab space, which means we are converting that into a layer that contains the lightness information, which is a black and white image, nothing but a black and white image. On top of that, we are actually adding color using 2 axes. One axis going from green to whatever that color is, let's call it red, looks deep pink to me, and the other one goes from blue to yellow. Okay, so this is pretty much it. And as you can imagine, when we are guessing, we are artificially coloring our images, all we are trying to predict is this space, yeah, and apply that on top of our light images. Please don't get confused. Well, hopefully I can clear any confusion by going through the code here. Okay, so step 1 again, right after resizing your images, I should say step 2, after resizing your images, is to convert RGB to lab space for the reason I just mentioned. And as I also mentioned just now, we are assigning the L channel, which is the black and white image channel, to the X vector. And again, if you remember, again, let's go back to our PowerPoint presentation, just give you a quick idea. X here and Y here, right? So autoencoders, we are assigning X as X. I mean, now we are actually doing X and Y. And my Y here is the color, and X here is the lightness. That's exactly what I'm trying to define here. Okay. Again, I really don't want you to be confused, so let me explain. I'm prepared, as you can see. Let me explain this a bit further. If you look at my Mona Lisa image here, this is a color image, right? Now let me convert. I'm reading that image and converting that image into lab space by using RGB2Lab that's available in Scikit-Image. And now let's look at the 0th channel, or the first channel, which is our L. And then the second channel is A, and third channel is B. Let's map out our L here, okay? So as you can see, this is our black and white image. Okay, so this is what these pixels, or these values, are going to be our values that go into our X vector. Okay, when we do model.fit, and what goes into Y is A and B together. Okay, and let's actually look at A. It's not going to plot it in color because I'm just doing ImShow here. It's going to show it in gray. But think of this space going from, where does A go from? Green to red. If I actually map this in green to red space, that's the information that this channel actually contains. Okay, the B, very similarly, this is our B. So we are predicting A and B and adding that information to our L to convert a gray image into a color image. So that's the story here. Okay, now that we understand this, rest of this should be pretty straightforward. Again, my X and Y are empty arrays right now. I'm going to fill it with appropriate data. So I'm filling X with the L channel information, and I'm filling the Y channel with with 1 and 2, which is our A and B. Okay, and why am I dividing these by 128? Okay, now let's go back to our RGB image and look at LAB, right? So we converted this image into LA and B. If I open this L, look at the values. I believe L values go between, did this graphic mention anything about L? Yeah, they go from 0 to 100. Okay, and I don't think they mentioned anything about these values. Actually, the A and B values go from minus 127 to plus 128. I think in a way they kind of represented that. I don't know. Well, it's not mentioned here, but you just have to trust me. So L goes from 0 to 100. As you can see here, L is going, I mean, you don't see 100 pixel values there, but L goes from 0 to 100. Now, if you look at A and B, let me just open A first. You see there are negative values, right? Negative 11, and these are all like floating point numbers. So negative 11, and there are some positive values. So A and B, these values go from minus 127 to plus 128. But the activation function, obviously we cannot use ReLU, because ReLU activation function goes from 0 to 1, right? So we need something that goes from negative 127 to positive 128. The best way to do that is by normalizing all of my values to stay between negative 1 to positive 1, minus 1 to 1. Okay, that's exactly why we are dividing it by 128. Okay, so now my Y vector contains values between minus 1 to 1, which means again I cannot use ReLU activation function again. Okay, that's exactly why on the last layer, the prediction layer, we are using tan H activation function in our autoencoder. Again, tan H, go ahead and read about activation functions. There are numerous resources online. If I scroll down, you should see tan H right there, hyperbolic tangent, and it's going from, you see, minus 1 to plus 1. Okay, so that is exactly why we are dividing these pixels by 128. Okay, so after that, it's now I have my X array and Y array ready. In fact, if we run the code until this point where we are loading the data, we have 340 images. Okay, and we should see an array of 256, by 256 by how many ever classes there. Okay, so now if you look at our X array, our X is the shape of our X is we have 340 images. Each image is 256 by 256 by 1, right? This one is our L channel. The other one is 340 images, 256 by 256 by 2, and these two represent A and B channels. Okay, so now you can see how my Y is ready and our X is ready. Okay, so we now need to define our autoencoder, and here it is. Here is how I defined. Again, there are many ways you can define it, but do not forget, if you follow this approach, do not forget to make sure that your last prediction layer has two outputs, each corresponding to A and B, and using an activation function of tan H. So now let's go ahead and actually check this model like I always do. Go to my model checking and replace what I had here with the new one and go ahead and run it. Now this is again, this you can visualize your model here. My input is 256 by 256 by 1, right? This is our L channel that goes in, or the black and white image that's actually going in. And then after the first convolutional layer, 128, 128, 64, 128, 128, 128, there are a lot of parameters that are used in training. And I'm not using any max pooling or anything in between. So these are all convolutional layers, one after the other. And upsampling obviously comes at the decoder stage, because once the image goes down to 32 by 32, of course I need to upscale them back to 256. Okay, so that's why we have these upscaling steps down here. Finally, giving us an output of 256 by 256 by 2, so which means A and B channels that are actually reconstructed. So that's our autoencoder architecture. And then, of course, we are fitting the model with X and Y. Again, X is our L channel and Y is the information from our A and B channels. Okay, so we are training the image on black and white, converting it into the color on numerous images. So the hope is that, okay, we come up with a model that's trained on so many images. Now you can supply any other generic image and it actually colorizes in a very nice way, including the images of your grandparents from 60, 70 years ago. Okay, and let's go ahead and save the model. And once it's saved, let's go ahead and colorize other images. So we are all set to start. Let me is there anything else I should be explaining at this point? I think we talked about tan H, which is one difference between what we talked in the past. What else is there? I think we're all set, right? So let's go ahead and start, and I'll wait until it starts, and then we can switch to the other code where we can colorize an image. No point in staring at this screen for 5 epochs. There you go. So that's the printing of the model, and now the epoch 1 out of 5 actually started. You can see how slow this is. Even with 2 GB GPU, this is relatively slow. So let's not stare at the screen. Let me go ahead and kill this. I have trained using this. I've trained it for 300 epochs, and I saved it under the name Colorized Autoencoder 300. Okay, here we are actually loading the model. And now I'm just applying it to an image called sunset, and here it is. This is my gray image, sunset, and let's go ahead and colorize this. Okay, so again, obviously I need to convert that image to 256 by 256 in case it's not already that, and then do pretty much the same type of pre-handling, this data, convert this in, in this case, this is a black and white image, but then I'm converting it into lab color anyway. Okay, and then converting it back into RGB so we can actually have a look at it on the screen or when we save it. So let's go ahead and run this, and this should be pretty fast. There you go. What a beautiful picture, right? So this is my black and white, and here is the color. There you go, black and white color. Oh, nice sun. Okay, colored in orange. Let's try this on a different image. What else do I have in this folder? Let's try this barn. Okay, so I have an image of a barn. Let's change this to barn.png. Hopefully the barn would be in red. That's not bad. That's not bad at all. Okay, The sky is pretty nice and dramatic. I love this picture. I could have done maybe a better job in this area, but I don't know. Maybe in the original image that region is also like some brownish shade, but it actually did a pretty good job. Now it's going to do a horrible job if I supply a gray image of some portrait. Yeah, in that case, download a whole bunch of portrait pictures, train the model on portraits, and then you can colorize some of your black and white images that you have. So anyway, I hope you found this tutorial to be useful. Go ahead and try this on your own images, and this is a fun exercise, I would say. So thank you very much for your attention, and if you like this tutorial, obviously go ahead and like this video on YouTube and subscribe to my channel, because it always keeps me encouraged to create more such content. Thank you very much.